Hello everyone, welcome to my presentation. My name is Tingting. I am from State K Laboratory of Information Security. I am glad to introduce a note on the security framework of 2K DbHtS MACs. Our research object is Message Authentication Code. For short, we call it MAC. It is a fundamental symmetric key primitive to provide the integrity and authenticity of messages between two parties. That is to say, it can prevent the message from being tampered by other unauthorized users. MAC is a core element of real-world security protocols such as TLS, SSH, or IPsec. Let's see how MAC works. There is a sender and a receiver. They share a secret key. If the sender wants to send a message to the receiver, he firstly computes the tag of the message by the MAC function, which is keyed by the secret key. And then he sends the message and its tag to the receiver. The receiver receives the message and the tag. She imports the message into the MAC function again and gets another tag. Then she verifies whether or not the message is valid by whether the two tags are equal or not. The equality of them means the message is valid. Then the receiver accepts it. Or the message has been tampered by other unauthorized users. She discards it. Then we define the security of MAC by an experiment. In this experiment, we replace the receiver with an adversary who doesn't have the secret key. The adversary can query stacks of messages many times. We say a MAC is secure if any adversary can't forge a valid message tag pair. MAC is often designed to be a pseudorandom function. For short, we call it PRF. It is difficult to forge for a PRF. Therefore, such MAC is secure. Framework can unify the proofs of the different MAC schemes. Several frameworks have been proposed. Simple MAC schemes, including ICICS, PMAC, HMAC, and NMAC, follow the hash-then-fixed input length function framework. For short, we call it HTF. See the picture. 1H is an almost universal hash function, and E is a fixed input length PRF, often instantiated as a block cipher. Then, HTF is a n-second bit secure PRF. That is to say, the adversary needs to make about 2 to the power of n-second queries to distinguish it from a random function. Are there other frameworks can be more secure? Yes, 3K double block hash-then sum framework, generally shortened to 3K DbHtS, is the sum of two independent HTF frameworks with twice the length of the internal space. See the picture. So it achieves higher security. It covers the proofs of many MACs, including SUM-ECBC, PMAC+, 3K F9, and Light MAC+. In this framework, we treat the two block ciphers with independent keys as two independent pseudorandom permutations. At Crypto 2018, Leonard et al. Gave an attack against it with about 2 to the power of 3 enforced queries. At FSE 2019, Data et al. Proved when the two hash functions are weak cover-free and weak block-wise universal, the 3K DbHtS is 2 n-third-bit secure. And at Eurocrypt 2020, Kim et al. Proved when the two hash functions are almost universal, it achieves the tight 3 and 4-bit security. This framework uses the hash key and the true keys for block ciphers. Can we reduce keys? Yes. At FSE 2019, DbHtS et al. Proved when the two block ciphers use a same key, if the two hash functions additionally satisfy cladding property compared to 3-key DbHtS. The framework also achieving 2 1/3 bit security. They call the framework 2-key DbHtS. All the former frameworks are in the single user setting. It is a limit, because in practice, the adversary can attack multiple users. For instance, MACs are core elements of real-world security protocols, which are used by lots of websites with plenty of daily active users. So it is necessary to consider the security in the multi-user setting. Now we introduce the multi-user PRF. Take function f being 2-key DbHtS as example. There are two systems. One is the real system S1, consists of many f functions with independent keys and its underlying block cipher. The other is the ideal system S0, consists of many independent random functions and block cipher. If there is no adversary can distinguish the two systems, then the function f is a multi-user PRF. At Crypto 2021, Shen et al. Revisited the security of the 2-key DbHtS framework in the multi-user setting elaborately, and showed their conclusion in Theorem 1. 1. The two hash functions are both regular and almost universal. For short AU, and the block cipher is an ideal cipher, then the 2-key DbHtS is a PRF, where optional 1 regular means for any x and y. When the hash key is chosen uniformly and randomly from the hash key space, the probability of the hash key with input x outputting y is no more than optional 1. Optional 2 AU means for any two different x and x prime. When the hash key is chosen uniformly and randomly from the hash key space, the probability of the collision of the hash function with input x and x prime is no more than optional 2. According to Theorem 1, where optional 1 and optional 2 both about 1 out of 2 to the power of n, then the PRF should achieve 2 1/3 bit security. However, we point out that their framework has a critical flaw by giving 3 counterexamples. In our examples, the two hash functions also satisfy regular and AU properties, and the examples based on them should be 2 1/3 bit multi-user secure 2-key DbHtS MACs, according to Theorem 1. But we find they exist true to the point of n-second queries attack even in the single user setting. It is a contradiction. We also show clearly the miscalculation in their proof leading to such a flaw. Let's see the first counterexample, whose hash functions handle fixed input length. The hash function h1 using kk1 with input m is m exclusive k1, and the hash function h2 using kk2 with input m is m exclusive k2. Assume the size of the block cipher is n bits for these two hash functions for any m and y. When the hash key is chosen uniformly and randomly from n bits space, the probability probability of the hash function hi with input m outputting y, that is to say, m exclusive ki equals to y, is no more than 1 out of 2 to the power of n. So h1 and h2 are 1 out of 2 to the power of n regular. And for any two different messages m and m prime, when the hash key is chosen uniformly and randomly from n-bit space, the probability of the collision of the hash function hi with input m and m prime, that is to say, m exclusive ki equals to m prime exclusive ki, is equal to 0. Thus, h1 and h2 are 0 AU. So, according to Theorem 1, this example can be proved to be 2n third-bit multi-user PIF. Now we show it exists 2 to the power of n second queries attack even in the single user setting. In fact, our example has a secret period key1 exclusive key2 in its import. After the adversary make about 2 to the power of n second queries with messages 1, m1, m2, and so on, it can find a pair m and m prime for which the output of the first hash function with m collides with the second hash function with m prime. Meanwhile, the output of the second hash function with m must collides with the first hash function with m prime. So the function f with these two messages have the same output. That is to say, the adversary finds the period, which is equal to m exclusive m prime. However, random function has no period, so the adversary distinguishes them. Compared with the first counterexample, our second counterexample can handle variable length input. Its hash functions are keyed polynomial functions. And the third counterexample is based on block ciphers. Its hash functions are true CBC max without the last block cipher call. Assume the block size is n bits. For these two examples, the hash functions are both L out of 2 to the power of n regular and L out of 2 to the power of n AU, where L is the maximal length of the message blocks. According to Theorem 1, they are also proved to be 2n third-bit multi-user PIF, where they exist about 2 to the power of n second queries attacks in the single-user setting, similar to the first example. Before we show the miscalculation in their proof, we give an overview of the proof of Theorem 1. Shen et al. Used the H-coefficient technique, so we have a look at it. When considering the interaction between an adversary and the real system S1 or the ideal system as S0, let Mi denote the query from the adversary to the system, and Ti denote the response of Mi from the system to the adversary. Then, the resulting interaction can be recorded with a transcript tau, which equals to M1 T1, M2 T2, M3 T3, and so on. Let PSI tau denote the probability that Si produce tau. Di denote the distribution of the transcript in Si. Then, by H-coefficient technique, the upper bound of the advantage of any adversary distinguishing the two systems is epsilon as the probability of D0 is bad. where for any good transcript Tor set P(S1) Tor out of P(S0) Tor is no more than 1 minus epsilon. So their steps of the proof to prove theorem 1 are as following. Firstly, they divided every transcript Tor to good or bad. They defined Tor is bad if it is easy to distinguish the real system S1 from the ideal system S0. Otherwise, it is good. There are 14 bad cases, bad 1, bad 2, until bad 14. Second, they computed the probability of D0 is bad, whose upper bound is the sum of the probability of these 14 bad cases. Then, they computed the ratio. Now we point out their miscalculation in their proof. When they computed the probability of bad 9, that is to say, the probability of simultaneous collisions of the first hash function with message m and the second hash function with message m prime, and the second hash function with message m and the first hash function with message m prime. When the two hash keys are both chosen uniformly and randomly, they regarded the two collisions are independent from each other. In fact, it may not hold. The three counterexamples before all satisfy that when the first collision happens, the second collision will happen too. We summarize our report. Firstly, we point out a flaw of the security framework for 2K DbHtS in the multi-user setting proposed by Shen et al. By constructing three counterexamples. Secondly, we also analyze how the flaw happens in their proof. This is due to the fact that the authors overlooked the dependence of the two hash functions. Later, Shen et al. Refined their paper because of what we have found, and Data et al. Proved 2K DbHtS framework where the two hash functions have split ranges, even achieved 3 and 4-bit multi-user security. The two hash functions with split ranges avoid the flaw which we proposed. These are the main references in this report. Thanks.